Hello students, Callie Daniels here. In this video we'll take a look at further applications of linear equations. In example 1 we're going to solve a classic mixture problem. Here we have a certain metal that is 40% copper. How many kilograms of this metal must be mixed with 80 kilograms of a metal that's 70% copper to get a metal that's 50% copper? I'm going to use some pictures to get us started. And let's suppose that we have some containers of a metal, okay, and this is probably in a liquid form here. And this first metal is 40% copper. And we're going to mix it with another metal. So here's our second container, containing 80 kilograms of a metal that's 70% copper. And we know this amount to be 80 kilograms. And together, when we mix these, we're going to obtain a metal substance that is 50% copper. Now, our question is how many kilograms of the 40% copper is going to be mixed in? So we are going to let X represent the amount of the 40% copper metal substance. Okay, and we just put X in the picture. That's going to be in amount in kilograms. Now, notice in each picture we've got a percent and an amount. Percent, amount, percent. We need an amount here, don't we? Now, if we add 80 kilograms to X kilograms, we can express the amount of the mixture as X plus 80. And that's an amount in kilograms. Now, if you can draw this picture, then you've got the problem whipped, okay? So now we're going to multiply through these pictures to form an equation. And it's all going to be based on the amount of copper, okay? How much copper is in this 40% metal substance? Well, 40% of X, okay? In other words, 0.40 times X. 40% of something, we multiply it times 0.4 or 0.40. What is 70% of 80? We determine that by multiplying 70% in its working decimal form as 0.7, or you might say 0.70 times 80. And that should be equal to the amount of copper in the mixture, okay, which is going to be 50% of X plus 80. Okay, now we've got our equation. We're going to solve it. Now in this problem, I am going to multiply each side by 10 and eliminate the decimal values, just to show you how that's done. Now we're going to distribute that 10 to each term. Okay. Well, 10 times 0.4, moving the decimal point one place, becomes 4. That's 4 times X. 10 times 0.7, moving that decimal point one place, is 7. Take that product then times 80. Don't mistakenly apply the distributive property there. There's no plus symbol in here. We're multiplying three things. We can do that in any order that we want to. Okay. Same over here on the right hand side. 10 times 0.5 is 5. And then we take that product times X plus 80. Now let's solve. We have 4x plus 7 times 8 is 56, so 7 times 80 must be 560. Distributing on the right, we have 5x plus 400. I'm going to subtract 4x and subtract 400. So x must be 160, that's kilograms of the 40% copper metal. Now, something to note here about all mixture problems is that when you mix a weaker substance with a stronger substance, you're going to get a mixture with a percentage in the middle. Notice that 50% is between 40 and 70%. That's always going to happen. Also, let's remember that we can check these solutions. I'm going to go ahead and check this. Is 0.4 times x, replace x with 160, plus 0.7 times 80 equal to 0.5 times 160 plus 80. Okay, now 0.4 times 160 is 64. 0.7 times 80 is 56. And is that equal to half of 240? And this is going to work out because, yes, we get 120 is equal to 120, and that checks out just fine. That's the classic mixture problem, and I recommend pictures to help you summarize your information. Now, example 2, we're going to solve a classic simple interest problem. And we're going to need to use the formula interest is principal, amount invested, times rate of interest earned, times time in years. And in your interest problems in this chapter, your time amounts are always going to be 1 year. So t is going to be equal to 1 for all of these. I'll just let you know that up front. Now I'm going to use a table to organize our information for this classic interest problem. And I've just put principal, rate, time, and interest earned. All right, here we go. With income earned by selling a patent, an engineer invests some money at 5%. That's a rate, right? 5% in its working decimal form. And 3,000 more than twice as much at 8%. The total annual income that tells you that this investment is for 1 year. That's our time amount. And we know that the total income, and total gets from adding a couple things together, is $1,710. Now, our question is, find the amount invested at 5%. Okay, that amount is the principal. So I'm going to put our variable right here in the principal column for that 5% investment. And let's read through here again. We know that 3,000 more than twice as much is invested at 8%. So 3,000 more than twice as much we can express as 2x plus 3,000. And that's really the trickiest part of this problem. Now we're going to use our formula to determine our interest amounts earned. Multiply your principal times rate times time. And I'm going to write the 0.05 as our coefficient in front of x. Same for our second row, principal times rate times time. And we're going to write this as 0.08 times 2x plus 3,000. Remember, multiplying times 1 doesn't change anything, okay? So we're relatively ignoring that. Now we know that the total of these investments, the total interest earned is $1,710. And there comes our equation. The interest earned at 5%, which we call 0.05x, when added to the interest earned at 8%, 0.08 times 2x plus 3,000 is equal to $1,710. And there's our equation to solve. Now, previously in example 1, we eliminated the decimals. I'm just going to leave them in this time. You have the choice of working with the decimals or eliminating them. It's up to you. Okay, so I'm just going to leave them in this time. Here we go. 0.05x plus, as we distribute 0.08. 0.08 times 2x is 0.16x. 0.08 times 3,000 is 240. Combine our like terms. 5 and 16 is 21. That's 0.21x plus 240 is equal to 1,710. Let's subtract 240. 1,710 minus 240 is 1,470. And divide that by 0.21 and you'll get 7,000. So, how much was invested at 5%? Our answer there is $7,000. Make sure you get your units on there. And if you want to run a quick check, then just plug this into your original equation is 0.05 times 7,000 when added to 0.08 times 2 times 7,000 plus 3,000. Is that going to give $1,710? And it does, and I'll let you finish that check, okay? We can always check these in our original equation. When solving simple interest problems, you are going to have to know the formula I equal PRT, and I recommend a table to help you organize your information there. As we look at example 3, we're going to solve this problem involving distance, rate, and time. In part A, we know that the speed of sound is 1,088 feet per second at sea level when it's about 32 degrees Fahrenheit. So speed of sound depends on elevation and temperature, interestingly enough. In 5 seconds under these conditions, how far does sound travel? Well, to solve distance, rate, and time problems, we need to know the formula distance is equal to rate times time. In this problem, we're just going to substitute the values that we know, okay? We're asked how far, okay, so find the distance, okay? Our rate is 1,088 feet per second, and per is a division word. And our time is 5 seconds. So we're going to multiply that by 5 seconds. Now, I've left the units in here so that you can see how they divide out. Seconds in the denominator divides out seconds in the numerator and leaves our units here in terms of feet. And 1,088 times 5 is 5,440 feet. So under these conditions, sound travels 5,440 feet in 5 seconds. Okay, that's approximately a mile. So when you're listening to that thunderstorm and you hear the thunder, if you can count slowly to 5, about 5 seconds, 1, 2, 3, 4, 5, okay. So actually when you see the lightning, if you can count to 5 before you hear the crack of the thunder, then that lightning was about a mile away. Okay, for every second that you can count, that lightning was about 1,100 feet away. So if you see the lightning and hear the crack right away, run for cover. Okay, it's really close. Let's look at part B. 2 airplanes leave Boston at 12 noon and fly in opposite directions. One flies at 410 miles per hour. The other 120 miles per hour faster. So 410 plus 120 is 530. So it's flying faster, isn't it? Okay, so it's going to go a little further than the plane that's flying slower. How long is it going to take them to be 3,290 miles apart? So at what point in time is the sum of these two distances 3,290? And that's approximately the distance across the continental U.S. Now, Boston's up there in the northeast, so somebody's probably flying out over the ocean. But anyway, we are going to have to rely on the formula distance is rate times time. I recommend using a table with headings for rate, time, and distance. We know the rates are 410 miles per hour and 530 miles per hour. The question is, how long does it take for this to happen? So I'm going to use the variable t for this unknown time. going to multiply rate and time to get an expression for each distance. 410 times t and 530 times t. And we're going to add those two distances together to get a total of 3,290 miles. So this is a distance problem where we're going to add two distances. So 410 times t, the distance traveled by the slower plane, plus 530 times t, the distance traveled by the faster plane, is going to total 3,290. And if you can make it to this point, then hey, give yourself a pat on the back and just solve the problem. 410 plus 530, that's 940. T is 3,290. And divide by 940. And I'm going to go ahead and write this in decimal form as 3.5 hours. This is an application. If you want to write that as 3.5 hours, that's fine. Okay, I'm going to say 3.5 hours. So it's going to take 3.5 hours for them to be 3,290 miles apart. And just run your quick check, okay? Plug it in. Is 410 times 3.5 when added to 530 times 3.5 really going to give 3,290, and it does. We get 1,435 plus 1,855, and that's 3,290, and this is going to check out just fine. Well, let's look at one more distance problem. Our last problem for this video, similar to part B. At a given hour, two steamboats leave a city in the same direction on a straight canal. So our picture here is going to be a little bit different than previous, okay, because these steamboats are going to be going in the same direction on a straight canal. One travels 18 miles per hour and the other 24 miles per hour. And since it's going faster, it's going to travel further. In how many hours will the boats be 9 miles apart? So when is this difference between their distances going to be 9 miles? So in this case, we're going to subtract distances, where previously we added them together. How do we know if we're going to add or subtract the distances? You've got to draw a picture and make sense of the problem to know. I'm going to go ahead and use a table again to summarize information. The rates are 18 miles per hour and 24. We're solving for time. That's the question asked. We multiply rate times time to get an expression for these distances. And we're going to subtract the distances. And we know to subtract in this order: 24t minus 18t, to obtain that difference, 9 miles. Because the faster boat travels the further distance, so we know to subtract in this order: larger distance minus the smaller. All right, well, that difference, 24 minus 18, is 6. 6t is 9. Divide each side by 6. 9/6 reduces to 3 halves. 3 divided by 2 is 1.5. So 1.5 hours is our answer, and go ahead and check it. Is 24, checking in our original equation here, okay, times 1.5. From that, if we subtract 18 times 1.5, are we really going to obtain 9? In other words, is 36 minus 27 equal to 9? And it is. All right, now in this video, we've seen the classic mixture problem, interest problem, and 3 very typical distance, rate, and time problems. You will need to know the formulas. Distance equal rate times time. Commit that to memory. Interest equal principal times rate times time. It's another good one to have in your back pocket. All right. Good luck on these.